Welcome to mathematics, and we are in a new topic, that is properties of triangles. So till now we have been looking at trigonometry from a right angles perspective, right? In order to define all the six ratios, we are defining them only in a right angle triangle. When theta is one of the angle in a right angle triangle, then we said sine theta is the opposite side by hypotenuse, cos theta is the adjacent side by hypotenuse. Like this, all the six ratios are defined in a right angle triangle. But if you remember, in the beginning of trigonometry, we said trigonometry is the study of a triangle with its sides, whereas there is no restriction as such for a right angle triangle. Now this is the topic which extends the definitions of all the six trigonometric ratios in terms of any general triangle. That is, the triangle need not be a right angle triangle now. We can still define sine of an angle, cosine of an angle of a general triangle in which none of the three angles are right angles. Study of the relation between the angles of this triangle with that of the sides of the triangle is called as properties of triangles. This is actually an extension of a right angled trigonometry study to a general trigonometry study. Now let's begin the session 1, and in this session what we are going to do is initially we'll try to review all the notations that we use in this topic in our further study. We'll learn different notations that come across, and then we'll try to find out the area of triangle, not in terms of sides of the triangle which we know already, but now in terms of trigonometric ratios. We'll try to find the area of the triangle, and then we'll derive an important rule called sine rule in a triangle. And with the help of this sine rule, as an application of this, we'll try to find the lengths of internal angular bisectors. So let's begin our study with notations. Now in any triangle ABC, in general, the vertices A, B and C are denoted by the capital letters, right? And then if you observe the diagram, we have taken vertex A in red letter and small a is also taken in red letter. With the side BC, the length is also denoted in red coloring. Now what do we mean by this? This side opposite to the vertex A is of length small a. And in order to stress this fact, that's why we maintain vertex name, the side length and the side which it denotes, all three in a same color, so that there will be no confusion. Throughout this topic, whenever we say capital A, it is the vertex A. Whenever we say small a, it is the side which is opposite to the vertex A, that means BC. Now similarly, B denotes the vertex of the triangle, then small b denotes the side opposite to vertex B, that is AC side, right? So small b is the length of AC side. Similarly, capital C denotes the vertex C, then small c denotes the side which is opposite to the vertex, that is small c will be equal to the side length AB. So try to remember this procedure. Capital A is the vertex, small a is the side opposite to the vertex. Similarly, capital B is the vertex, small b is a side length which is opposite to the vertex B. Capital C is a vertex and the side opposite to that is denoted by small c. Even the colors were so chosen that each vertex and the corresponding side opposite to that will be maintained in the same color, right? Similarly, whenever we say angle A, angle B and angle C, we refer to the interior angles of the triangle. That means the angle at this interior part of the vertex A, this is denoted by angle A. Similarly, the angle at the vertex B, that is interior angle at B, is denoted by angle B. And the angle existing at the vertex C, the interior angle, is denoted by angle C. Right? So capital letters denote the interior angles. Remember this, very important. Now similarly in the triangle, the semi-perimeter, that is half of the perimeter. Do you remember what is semi means? Half of. So half of the perimeter is denoted by S, small s, and it is sum of the three side lengths A plus B plus C, that is BC plus CA plus AB by 2. That denotes the semi-perimeter of the triangle. Wherever we use small s, it denotes the semi-perimeter of the triangle, and the value is given by half of the perimeter, that is small a plus small b plus small c by 2. Now similarly, the area of the triangle is denoted by delta. Delta always denotes the area of the region. And these are triangular inequalities in a triangle. Each side of a triangle is less than the sum of the other two sides, isn't it? That is the triangular inequality in a triangle, right? So similarly here also, the side BC should be smaller than the sum of AC and AB. So A should be less than B plus C. Similarly, the side AC must be less than the sum of the other two sides BC and AB. That is, small b should be less than C plus A, and the third side C must be less than the sum of the other two sides, that is AC plus BC. So each of the side in a triangle is smaller than the sum of the other two sides. Now similarly, there is one more form of triangular inequality. Each side must be greater than the difference of the other two sides numerically. So that's why mod A must be greater than the difference of the other two sides, that is B minus C. The B must be greater than the difference of the other two sides, C minus A, and C must be greater than the difference of A and B, right? So these two rules are also known as triangular inequalities in a triangle. The sides are related to each other by these inequalities, right? And a well-known result from geometry, the sum of the three interior angles of a triangle is always a straight angle, that is 180 degrees, right? Now these are some of the notations which we also use in terms of the circles related to a triangle. Now capital R would always denote the circumradius of the triangle. That is, for a triangle, when you draw a circle which is circumscribing it, how does it look like? Yes, a circle which is passing through all the three vertices of the triangle. Such triangle's radius is denoted by capital R. The circumradius is denoted by capital R. Now small r denotes the inradius of the triangle. How will be the inradius? The circle which touches all the three sides internally, right? So this circle which touches all the three sides of the triangle internally, the radius of this circle in this chapter would be denoted by always small r. So small r denotes the inradius of the triangle. Now what are these? R1, R2, R3 denotes the x radii opposite to the vertices A, B and C respectively. Now what do we mean by this?